Good morning, dear colleagues. I'm Haris Kontoes, the coordinator of the Disaster Resilience Showcase of the eSafe project. I'm delighted to be with you and thank you for your kind attendance. This session presents the pilot and the progress of the pilot in the showcase. Special attention will be given to the level of maturity and the innovation aspect of the delivered services with respect to the current state of the art and the extent by which the engaged sectors are benefiting from it. Let me share my screen. I have a small presentation to introduce you in the showcase for disaster resilience. The main driver for defining the specific showcase is the widely recognized need for rendering sectors and societies resilient to disaster, natural, and human-induced hazards. According to the official numbers from UN, disasters cost hundreds of billions of dollars, hitting the poorest countries disproportionately and pushing millions into poverty. As Antonio Guterres, the Secretary General of United Nations Secretary states, we must start disaster risks and leave a more resilient planet to future generations. Today, disasters drive 26 million of people into poverty every year. In year 2017, it was stated that 18 million of people were forcibly displaced by extreme weather events linked to climate change. And we know that in the period 1998-2017, billion of people have been affected by disasters, 2 billion from floods, 1.5 billion from droughts, and many million people from other types of disasters such as earthquakes, storm surges, extreme temperatures, landslides, wildfires, volcanic activity, and many other types of disasters. After 6 years of continuous drought in Guatemala, Honduras, El Salvador, and Nicaragua, 2.5 million left without food and 3.5 million of people left without income. In the years 2011, 2017, and 2019, prolonged drought in Ethiopia, Kenya, and Somalia affected more than 15 million of people and left them without food and water. In 2019, the cyclone Idai hit Zimbabwe, Malawi, and Mozambique, leaving many million of people homeless and without food, and more than 10,000 of people killed by the storms. In the last years, in the last decade actually, big wildfires hit cities over the world. In 2015, 2017, and 2018, many people have been affected. 3,000 houses totally destroyed by flames, and we had 86 people dead by the fires. And in Australia in 2019, the unprecedented drought and high temperatures that occurred in the country, in the continent actually, had resulted in a full destruction of more than 12 million hectares of wildland, with many impacts to the ecosystems. In this suffering world, resilience could not be other than a portfolio of innovative services so as to face and mitigate natural and human-induced disasters, according to the priorities set by the SEDAI framework for disaster risk reduction and according to the targets as they have been set by the Agenda 2030 for Sustainable Development Goals. The focus of the showcase for disaster resilience is to set an effective strategy for building successful innovative services. We develop services towards supporting the daily practices, not only of civil protection authorities, but also of important economic sectors. Therefore, much emphasis has been put to the support of business continuity and the resilience of societies, but also of economy drivers, such as agriculture, energy, critical infrastructure, and facilities management industry. Before I give the floor to the speakers of the session, let me just recall the 4 pilots of the showcase in the order they will be presented. The pilot 1 deals with the use of the Earth observation data for detection, discrimination, and distribution of volcanic ash. In the pilot 2, satellite data with the mass of in situ and sensor data are combined so as to enhance the modeling for hydrometeorological hazard prediction. The pilot 3 is using satellite data processed by the interferometric synthetic aperture radar techniques so as to assess the geo-hazard vulnerability of cities and critical infrastructures. And pilot 4 is it's building services dealing with the use of the Earth observation technology and weather modeling to render the agricultural ecosystems resilient and minimize the impact of disasters in the agricultural sector. This is the agenda of this session, and I will directly give the floor to Pablo Ezquerro from EGS, who is presenting the pilot 3 activity assessing geo-hazard vulnerability of cities and critical infrastructure. Pablo, the floor is yours. I stop sharing the screen, and please share your presentation with our audience. Thank you.
Okay, thank you, Harris. I'm going to share my screen. Oh, here. Okay. Well, I'm going to present the working methodology that and the first results that we have developed for this pilot 3, assessing geohazards vulnerability of cities and critical infrastructure. The objectives of the pilot are to increase the use of multi-mission Earth observation-derived products and services to assess urban vulnerability and geohazards. Also to systematically map vulnerable areas and critical infrastructures threatened by geohazards, and last, to raise the early awareness and train key users and decision makers on the use of Earth observation derived products and services, increasing with this the urban resilience against geohazards. Our methodology to reach the objectives is based on exploit the available INSAR software, especially DS-GEP-TEP, to derive displacement maps based on the displacement on those displacement maps. Derive products and services to identify urban areas vulnerable to geohazards, and also in the last part is to disseminate these products and services first to the engaged key users and then all the community of potential users. At this point, we have developed 4 products with different levels and requirements, and these products are designed to be useful both for technical personnel, in the case of the first 2 ones that are the INSAR processing and the INSAR validation report are more technical, and the second ones that are more focused on the non-expert managers and decision makers, which are the urban vulnerable areas and the active geohazard areas, which products are more analyzed and the results are easier to understand for those people that have to take the decisions, and because they are usually not used to these technical products. At the okay, first and second products are the INSAR raw data and the INSAR validation report. They provide the main displacement data information about the performance and of the processing and a first assessment of the possible active geohazards. The active geohazards report is one of the main advanced products where raw displacement data are analyzed to identify the active deformation areas through a statistical analysis of the INSAR point cloud, and then crossing them with geohazard data like geological maps, land cover maps, the lines of the roads or the railways. With all those maps, we try to describe the specific geohazard that is taking case in the active area. At this point, we have designed a specific methodology for landslides and for subsidence, but we are also working in a methodology for mining areas, active and mining areas under rehabilitation process, and also for other triggers or other causes that could be related to overloading by building or natural subsiding processes. But these methodologies are not yet finished. Now we are working with the key users to define test areas with those processes in order to improve the description of these methodologies in their areas, and with the key users co-design this product with them. Well, the reporting in the areas with subsidence due to groundwater extraction in this case is based on the comparison of the deformation, the aquifer system behavior, and the human extractive activities. In the case of the landslide areas, the report focuses on the spatiotemporal characterization of the displacement. The fourth product is the vulnerable areas report. This product, supported by cadastral and damage information, allows to identify the vulnerability of the buildings based on the insert displacements. In order to show better the possibilities of this methodology, we have applied it to the Murcia City and Alto Guadalentín aquifer systems, which are an area affected by land subsidence. And this example has been used to co-design the global methodology and the specific methodology for groundwater or land subsidence due to groundwater extraction with the groundwater authority of Segura River and by the Spanish Geological Survey. First, the INSAR raw results, are highly dense point clouds depending on the processing resolution and local vegetation typology. This data can show a clearly deformed area like in this picture, or only small and slight displacements which are more difficult to analyze. Also, this data more dispersed in the area can be clustered to improve their management with some tools that we have proposed in the methodology. Over this area, we have also deployed a monitoring system, an additional monitoring system to insert data in order to validate the insert data. In this case, we have used GNSS permanent stations and leveling data. And also we have also combined two different types of insert data, but it's the most important part are the in situ data, which are the GNSS and the leveling. This kind of validation needs of contemporary and continuous data sets that are provided by those GNSS and leveling measurements, and the validation products will provide the root mean square error and the relative error of the displacement velocities and time series. If this kind of data is not available in other case studies, or they are not continuous or contemporary, the insert validation has the insert validation report has been designed to have other other types of validation that are partial or qualitative validation that provide a not perfect validation, but still important, especially for the interpretation of the results. The Arctic Subsidence Hazard Report is composed by two different steps that define the area of influence of the extractive activity and the temporal evolution of the subsidence. First, using the extraction rates in the position of the wells, a first estimation of the most susceptible areas can be done. Finding the influence area of extraction is a vital parameter for the groundwater management that differs depending on the extraction periods, as you can see in the right side graphics that are in this slide. The upper one is the extraction period was very short, and all the subsidence is only reached 1 kilometer from the well field, and in the second one the extraction period was longer, and the subsidence reached 3.5 kilometers. This is very important for the managers because with this they understand the area that they are affecting, and also the area that they have to control and look if there is some damages in the buildings, there is some cracks in the roads, this kind of information that is very important for them. The evaluation of the groundwater and subsidence time series give also the possibility to identify the extraction and recovery periods and the inflections of subsidence if it happens. The correlation or not of them describes the behavior of the aquifer system and the extraction stress, especially useful also to improve this management. In this case, the right side graphics, we can see two kind of different behaviors. The upper one is in the center of the basin, where many cycles of extraction has been carried on, and we can see that the red line, the land subsidence, it has a continuous declining trend that indicates that there is a delay subsidence. Not it is related to the extractions, but it overcomes the extractive periods, and it has to be taken into account. Another behavior that we have observed in the edge of the basin is that the bottom graphics, we can see that the land surface is stable until the last extraction period, where the wells were pumped for first time. There we can see that there is a quick subsidence, very correlated with the extractions. This is also important for them because they can move the extractions between all their wells and try to mitigate the effects over the aquifer system and also over the land surface. Last, the Urban Vulnerable Areas Report is one of the most complex products because specific information is needed, and usually new damage detection campaigns are necessary to plan and carry on. Due to that problem, two different levels have been described. The most complex one is based on fragility curves, which are empirically built, combining INSAR data and field data, the damage campaigns, the damage observation campaigns, to evaluate the potential damage on buildings affected by land subsidence. Once calibrated, they provide the probability of a level of damage we can we can describe different levels of damages. It is small cracks or large cracks, or the total collapse of the buildings. In this case, there was only very small cracks, for example. But we can describe one different curve for each level of damage. And these curves give us the probability of this level of damage for each building. We can even calculate expected economical losses if enough economical data are available in the cadastral plots, or this is an economical data that is only available in some areas, depending of the databases. The other level only requires cadastral information and combine specific data of the case study in order to define displacement velocity and accumulated displacement thresholds to evaluate the damage vulnerability of each building. This is a lower level of the product, but this kind of product is more accessible for all the test sites. And last, all these products applied to the study area affected by land subsidence help to understand better the dynamic of the aquifer system and adapt the exploitation strategies. Using the co-designed products, our stakeholder, the Segura River Water Management entity, has adapted the pumping strategy, moving the extractions to the less affected areas, taking into account the wells levels and subsidence time series during the drought periods, and trying to reduce the effects. Also, the building vulnerability maps are one of the main thresholds to cut off the pumping in the area, because damages to the structures were detected in the area during previous periods, and now that product is one of the most, the cracks are the problem, and the product is one of the solutions to evaluate if they are doing the right things, or they are over-exploiting and causing some damages.
Pablo, excuse me, you have only 1 minute left.
Sorry?
1 minute left.
Yeah, I have finished. Yeah, this is the finish. So that's a fast overview of the current status of the pilot and the methodology proposed. And now we are working with the EGS partners to expand the methodology to other case studies that they have already proposed, and we are also trying to engage local stakeholders for those test sites, and also to extend the methodology to other geo-hazards and adapt it to the stakeholders, co-designing these products, changing a little bit the products to adapt more to their necessities. And that's all. Thank you so much.
Thank you very much. It's an interesting pilot activity, actually, and it's one of the pilots showcasing perfectly how Earth observation today, with the advent of the Copernicus missions, is useful for mitigating geophysical induced hazards in cities and built-up areas. So we will have the opportunity maybe later on in the Q&A session to ask you a bit more few things on that. So the next speaker is Nikos Papagiannopoulos from CNR, who is presenting the progress of Pilot 1, Earth observation data for detection, discrimination, and distribution of volcanic ash. Nikos, the floor is yours. Please share your screen. Thank you. Hello, Nikos, can you hear us?
Good morning, can you hear me now?
Okay, yes, we can hear you, thank you.
And you can see my screen, I suppose, right?
Yes, of course. Please, if you want, if you put it on the display mode only. Put in the full screen mode.
Okay.
Thank you.
So, this is Pilot 1. I'm giving this talk on behalf of Lucia Mona, who is coordinating this pilot. The pilot is entitled Data for Detection, Discrimination, and Distribution of Volcanic Ash. First, I would like to give you, my presentation more or less is going to be more informative. I'm going to give you an overview of on what we have done and what we would like to do in the future. First, I will start with the background and the motivation for this work. So, volcanic eruptions present a threat for aviation, and of course, certain interruptions can cause a big damage, a big financial damage. And because volcanic particles can cause a variety of damage to the aircraft, among of which it could be can be an engine failure. Since 1991, ICAO and WMO have set up 9 volcanic ash advisory centers with a mandate to operate a 24/7 operational service. VAC Toulouse and VAC London monitor the airspace in Europe. In 2010, the unprecedented crisis in 2010 demonstrated the need for new approaches to enable stakeholders in the aviation sector to obtain fast and accurate information. So this means that VACs are not enough, are not sufficient, and there is room in this area for other projects, for new ideas to come in and help and assist the decision making. So our pilot is focused on volcanic ash and the implications related to the aviation industry. The pilot is built on the legacy of a project called UNADIX AV, which aimed at providing a way to integrate multi-source data with respect to natural hazards. What is usually happening is that stakeholders in the aviation system require advanced information. And what it happens during a natural hazard phenomenon or even during a volcanic eruption is that the data are not available, the users cannot find them, the data are not coherent or consistent, are not well integrated, are not tailored for their use, and of course, sometimes, and as it happened in 2010, the profiles were not available, and information crucial for the decision making. So our objectives are here to prototype a system to integrate multi-source data and provide the aviation community with tailored information on volcanic eruptions. We want to enhance the forecasting of the volcanic dispersal, foster innovation, and mitigate ash-related impacts. Our challenges are mostly related to data. I have listed some of them, is the interoperability of the data security, data policy, and of course the computational time, how much time it's needed for the data to be given, to be delivered to the user. Our outcome would be a 4D visualization platform. Here, that I have prepared this slide, it shows a graph. This is the framework, as I call here, in a nutshell, where we have several data sources. We have ground-based data, we have satellite data, we have volcanic observatories, data coming from the volcanic observatories, and we have model data as well. This data should be transferred to the database. This database will homogenize data, will transform them if need be, and also this database will be the hub where the data will be exchanged. Also, this database can archive and transfer the data. You can see that the arrow here is not a one-way arrow, it's a two-way arrow. And the reason is that, for instance, volcanic observatories, data from volcanic observatories might be beneficial for or are crucial for a model initiation. Therefore, this data must be somehow directed again to the modelers so they can initiate their simulations. And then from the database, we have to send this data to the visualization platform where there we will have the distribution of the volcanic plume. And with this visualization platform will disseminate of the forecast or the alert, the tailored products to our users. A bit more in detail, I will break down all these data sources into distinct elements. So in ground-based, we have ELINET LiDAR data. From satellites, we will use SEVIRI, MODIS, and so on. Then we have volcanic observatories, they operate a multitude of advanced instruments for the early detection of the eruption. And we have also the models SILAM from the FMI and the FlexPart model run by the NOAA Institute in Athens. The visualization platform is the UNADIC AV platform, and the users can be the ATMs, air traffic management and traffic control, the VACs, National Meteorological Services, and I could say the community at large, the community interested in aviation operations. This is, before continuing, I would like to show you like a flavor of what this platform looks like. As you can see in this platform, it's totally interactive. I consider that it's user-friendly, where the user can see model forecasts, can see satellite images, can see ground-based information. And, you can see that you have the let's say the freedom to use the platform as you would like. So far, what we have done, we've met several times with the pilot partners, several meetings we have made, and of course, the coordinator of the pilot has been in contact with the co-designer. We collect data, we discuss on the data, we examine cases, we discuss on the cases. So far, we haven't found a golden case for which all the elements that I mentioned before, the data sources, are available. So are still, this point is something that is worries us, but we think that we are in a good shape. We have a methodology for an early warning system using a halo LiDAR near the source. We developed it, we haven't tested it yet. The database is up and running, and we have achieved the first milestone. When it comes to the dissemination activities, we report success stories and newsletters in the website of eShape. We have publications related to this pilot. Whenever we can, we bring eShape to workshops and conferences. Now we'll move on to some results, where we will take a complex case study related to an eruption in Etna. This case, more or less, I'm giving you this case because I want you what we could do, or how the process chain would work in case of an eruption. So what do we have? In May 2019, Etna erupted, injecting a volcanic ash and SO2. IMGV issued a red VONA report on that day, although this eruption did not affect aviation. You can see some photos from the actual volcanic and the VONA report as it is issued by the INGV in Italy. So here is some more data. This refers to the advanced instruments, the cameras that they have in order to monitor at the source INGV. But also we can see what is happening from up above. Satellites, of course, are there to monitor and follow the ash plume as it evolves in time. Here you can see, I think my cursor shows more or less the position of Etna, where you can see that the ash plume follows a north-east direction. And having this information, we can start running our models. This is a SILAM simulation on 30 May 2018, where you can see moderate to low volcanic ash emitted and following the track as the survey showed us in the previous slide. But then again, if we check on Tropomi, the SO2 observations, we can see that on the 3rd of June, we have some, we observed SO2 in the Mediterranean. We ran again our FlexPart SO2, in this case, simulations, when we can see that going from 31st of May until the until the 3rd of June, we see that the SO2 moves eastwards, affecting parts of Greece. Indeed, in the Hellenic station of Antikythera in Greece, observed a complex aerosol situation where you can see here measurements from that site where dust was observed in the upper layer is yellow box in the yellow box, whereas the purple box shows you where we believe sulfates originating from Etna were low lying in the Mediterranean. And also we have here, what is nice is that in the bottom graph I have the alert for desert dust and volcanic ash that would be beneficial for our pilot. And with this, I stop my presentation.
Thank you, Nikos. Thank you very much. It's indeed very interesting to see a pilot activity that becomes useful to the aviation industry, a key economic driver and sector. It is interesting also to see that in this pilot activity, the Earth observation data are very effectively combined with European infrastructure in situ data as ACTIS. Now, the next presenter is Antonio Parodi from CIMA, who is going to present the activity conducted in Pilot 2, relating to the use of EO and other data for disasters in urban environment, mainly hydrometeorological disasters. Antonio, the floor is yours. Antonio, could you please share your screen? Okay, thank you.
Okay,
can you hear?
thank you. I'm good. I'm going to share my screen.
Thank you. Great. We can see you now. Thank you.
Okay, thank you so much. So as I said, I'm going to present a short overview about the activity of the Pilot 2 in showcase number 6. The title is GEOSS for Disasters in Urban Environment. This Pilot 2 is involving as key partners NOAA, CIMA, and with some support from SATSHEN. And the overall idea is basically to try to understand through a set of case studies that we have identified if and to which extent the combination of Earth observation data, mainly provided by Sentinel, together with in situ weather station, possibly from authoritative networks or from personal weather stations, may help in getting a better prediction of extreme hydrometeorological events. So namely flash flood, windstorms, hailstorms, lightning storms, and also peri-urban fires. The pilot is benefiting of the support and advice and discussion with our two core co-designers, namely the Italian Civil Protection Department, which is also the reference institution for CIMA as foundation of this department, and also more at the regional level, the environmental agency of Liguria region. We have already identified, from a high-level point of view, a set of key users like EU decision makers, like geospace and security community activity. And we, for example, yesterday during the dedicated talk about shorter version of this file, we spoke a bit with DLR colleagues. What we are willing to do, well, a characteristic of CIMA Foundation, but of many research and operational hydrometeorological entities in the Mediterranean. So we know that the Mediterranean region is frequently affected by very intense, hardly predictable weather events, which are producing a large amount of fatalities every year and also severe socioeconomic damage. We have a set of tools already available, numerical weather prediction models, capable to produce forecasts at very high resolution, kilometer scale. The problem is that not necessarily having such high resolution, so the potential to go finer and finer is guaranteeing an adequate predictive capability of those extreme localized events. So there is always a quest for searching better initial boundary conditions to improve the quality of the forecast. And what it is already in place from a certain standpoint in many countries, including Italy, is the simulation of conventional observations into the model. But this is not necessarily enough to provide the kilometer scale description of the atmosphere. So what the pilot is willing to do is to try, for selected case studies, the assimilation of Copernicus Sentinel data and personal weather stations in the chain in order to improve the forecast. We are not starting from scratch in the sense that we have already in place operationally in our institution for the Italian Civil Protection Department our flow, including the WRF model with data assimilation, combined with two different model instances related respectively to 5 forecast, Risico model, and 2 flood forecast, the continuum model. And this chain is already published in its simpler form on the MyDeWeather platform, which is the reference civil protection platform used by the Italian Civil Protection Department and also endorsed by WMO at a more international level. This system, however, is not fully benefiting now of additional growing available observational data. And so the idea is basically in cooperation with the Italian Civil Protection Department and the other agencies, the regions that I mentioned, to make a step towards a better usage of the available data. And this is basically captured in this cartoon. We have pieces in the workflow, like the Risico model, like the continuum model, and the WRF model with conventional data simulation. I mean, for example, radar data, which are already TRL 8 and 9. So they are already operational. What we want to develop in the project through a set of case studies is basically the assimilation of Copernicus data and personal weather stations, and also to make, in a perspective of a market usage, the deployment of this workflow more flexible on whatever computing platform. So what we did in the meantime in the project has been, for example, migrating the execution of the Risico model for SFAR and the continuum model, the one for hydrological applications, to a Docker and container paradigm. So basically having a self-contained application that can be released on whatever cloud computing or eventually high performance computing facilities for execution. The goal of the project that we are targeting is also to make automatic the download of certain observational data, Sentinel and the personal weather station and in situ weather stations, that nowadays are a little bit more cumbersome. And most of our work will be to bring through a set of case studies the overall system to a TRL around 7. And the approach will be basically to test this workflow through a set of different data simulation exercises, having at the end of the day the validation of the Italian Civil Protection Department in order to judge the quality. What we did in the meantime, basically, we have tested in the meantime some preliminary results for a very challenging case that we had last summer in Italy. This event took place the 15th July 2020 in southern Italy, in Palermo, and was capable to pour down a very large amount of rainfall in few hours. The cartoon that I'm showing is basically the Italian country subdivided in different hydrometeorological alerting regions with different color codes. Yellow means basically that those areas were alerted with a minimum level of alert. Green means no alert. And as you may see, the Palermo area was basically not alerted for any major event. However, the story was a little bit different because that day, in between 13 and 60 UTC, a major rainfall event took place in Palermo, and it was capable to pour down something like 140 millimeters of rainfall in just 3 hours. The event was convective in nature. You see here lightning strokes in those 3 hours as collected by the WRF platform. And the event was, from a temporal point of view, probably one of the worst that a meteo forecaster may have to face, because no rainfall in the first part of the day, a very localized rainfall event in between 14 UTC and 16 UTC, and then no rainfall. And the overall rainfall depth was in the order of 145 millimeters. No operational model was capable to detect these events, so people could not be alerted properly, and major effects were observed in the city center with very large impact on the highways and on the all socioeconomic activity. We have for this event a very large amount of observational data in situ weather stations, but the very special characteristic of this event, thinking about the civil protection perspective, was that that day, Murphy law sometimes is really precise in getting applied. The national radar mosaic, this is a CAPPI of reflectivity at 3,000 meters, 9 UTC, was suffering because of a lack of data over Sicily. So basically, the national radar mosaic was blind in the hours antecedent the event and during the event, was blind over Sicily. So no availability of radar data. Still, we try to use the radar data at large over Italy as constraint for our model simulation. So basically what we did a set of different experiments using computing premises provided by another Horizon 2020 project, Lexis, and we are collaborating with those colleagues. And we performed a set of experiments in rapid update cycle mode, assimilating radar data where available over Italy and also in situ weather station. As you may see, the forecast is not at all perfect, because you remember the red strong area near Palermo, which means more than 100 millimeters in 3 hours. But at least we have some signal of localized convection activity over the area. And this is, from a civil protection standpoint, a very interesting message. Also because this forecast would have been available basically 2 hours before the occurred event. So still in an forecasting mode, potential useful. The physics behind the event was good, because you may see the also the lighting activity that was present in the region, not as strong as the one observed, but still triggering in the mind of a weather forecaster the message that something could happen around. And interesting enough, also the VMI, the maximum vertical reflectivity, was suggesting strong convection around. So the take-home message was that pushing the envelope in bringing down the model resolution at cloud resolving respacing and assimilating in situ weather stations, either from civil protection or from weather on the ground, even in the absence of radar data, we could improve the forecast. Then we did also a forecast with weather underground, and more or less the message is confirmed. So convection was predicted. less than the one observed, but still significant. And to the best of our knowledge, it is the first time that those data are assimilated in in kind of operational framework. You see here also convection through lightning activities, and also the simulation driven by personal weather stations available from the weather at the ground is giving a message about possible convection around. And also this simulation would have been available right in time for nowcasting purposes. I'm not here telling that this is the solution of all our troubles with prediction of very high localized events, but the message is that those data can be of some value. Next steps will be, and we are working on that, preparing the sentinel data, especially sea surface temperature and wind over ocean, to be assimilated into the model. The expectation is that especially sea surface temperature, being a convective summer event, can help in further improving the weather forecast. But the results will be available in the next talk when we'll have also performed this. This is all from my side.
Thank you very much, Antonio. From your presentation, we clearly see a pilot activity advancing significantly the content of the knowledge to be provided to a key stakeholder, to the Italian Civil Protection Authority. And all this by assimilating the large amount of data, satellite data, in situ data, sensor data. So it's a very interesting pilot activity, actually. And now I give the floor to the fourth speaker, who is Nikos Bartsotas. Nikos is going to speak about the use of Earth observation and weather modeling to render agriculture sector and agricultural ecosystems resilient to disasters, minimizing the impact of disasters in the agricultural sector. So, Nikos, the floor is yours.
Thank you, Haris.
Antonio, could you please stop sharing your screen? Okay, Nikos, please share your screen now.
Okay. Just a sec.
Presentation.
All right. So I hope you can see my screen now. I will be presenting. Let me close this one. I will be presenting an overview of the progress of our research during those first 15 months of the ESAPE project, and especially on Showcase 6, Disaster Resilience, and Pilot 4. Our target in this pilot is to develop smart agriculture services that will be beneficial for both the agro-insurance sector as well as farmers' associations. We started by some meetings with our main co-designers that I will refer to in the next slide, and we selected the region in the northeastern Greece, in Eastern Macedonia and Thrace region. And why did we choose this region? This is because it is both the second highest yield production area in Greece in terms of cotton crop, and at the same time, it is an area characterized by data scarcity. Only 2 meteorological weather stations were available over the area in urban areas, which expectedly are of no use in terms of providing spatial climatic variations at parcel level that the insurance company and the insurance sector wishes for. This is the cotton extent over the Rhodope region that we focus. And this data scarcity that I just referred to was our main problem. Neither radar scans nor long records of in situ observations were available, and this had a result that the insurance sector could only provide a uniform rate over this region and crop type when insuring some some parcels. Another problem we had is that currently there is a need to physically go and evaluate all reported damages from an agronomist, and this expectedly delays the payout procedure after a distraction, let alone that it dictates leaving a part of the crop intact in order for the evaluation to take place. Last but not least, there is a limited amount of information in terms of early warning, so it's quite difficult to consult the users in order to take necessary actions. Our challenge scientifically was how to effectively combine all Earth observational reanalysis in situ and numerical weather prediction data in order to provide a more sophisticated product and monitoring that will suit the agricultural needs. In terms of scalability, we constantly try to expand our user segment that will benefit from the product development. And our main co-designers is Inter-American, which is one of the largest private insurance companies in Greece with more than 1 million customers, individuals and companies. And through the last decade, they paid out over 3 billion euros in claims. So this is a very important co-designer. And Yeti, which is a company that incorporates 71 farmers associations and offers also financing and technological solutions that aims towards providing innovative services to users and farmers. The 3 pillars under which we decided to work have 3 time scales, past, present, and future. And the first one provides the historical hazard, the vulnerability and risk over the area. For the present scale, there is a damage assessment and high-level monitoring suite. And for the future, we implemented a numerical weather prediction model as an early warning system. For the first part, in order to provide the historical risk over the region, we relied upon atmospheric reanalysis datasets available under the Copernicus Climate Data Store, namely ECMWF's ERA5 and ERA5 land, and we combined them with CHIRP's precipitation data that blends satellite observations with in situ measurements from rain gauges. And in order to have the vulnerability aspect, we were very thankful to receive a damage record from ELGA, which is the public authority for insurance that farmers are mandated to use in Greece, and private insurance is on top of that. So the combination of those two provided, and here you can see a visualization. On the left part is the historical hazard from heavy precipitation events that induced flooding. And this is actually a combined product with heavy precipitation events and maximum precipitation accumulation within 48 hours above the region. And the shaded area is the cotton crops. And here is the vulnerability from a 10-year record that I mentioned. And the combination of those two provides the heavy precipitation event and flooding risk over the area. Respectively, this is the image from high winds that affect the cotton crops. These are the days, the frequency of days with wind gusts exceeding 17 meters per second within the cropping season. And here we have again the vulnerability. An important remark is that in this coastal area, we observe a high damage frequency that wasn't denoted from the hazard. And potentially the model reanalysis didn't capture it, but in the combination, it advanced the warning level over this area. We also have the combined hazard from temperature, from heat waves and frosts, as well as the vulnerability from hail, which can heavily affect ball quality and overall plant health. We only have vulnerability here because in order to estimate the hazard, you need to have radar scans or very high resolution numerical weather prediction simulations that provide metrics such as convective available potential energy upon which you can judge hailstones. These weren't available over the area, so in this aspect, we stick to the vulnerability maps. Now, in terms of the present status, we have a development from our partner Neuropublic that combines observations from a relatively sufficiently dense network. They installed 9 weather stations over Rhodope to represent each climatic zone of the region. And they combine this data from the sensors with high-resolution sentinel imagery, 10-meter resolution, in order to derive NDVI measurements at a parcel scale. And what they do is that they have a high-level image of the health of the parcel, judging upon the fluctuations of the NDVI. They compare the current NDVI value with a statistical range. They also have the 20th and 80th percentiles to compare with, and they cross-check this with the in situ sensor readings in order to define obvious distraction cases. And last but not least, we have the early warning suite. We invested upon two high-performance computing nodes that have 160 physical cores, 320 with hyper-threading. And we implemented a state-of-the-art numerical weather prediction system that provides 6-kilometer resolution forecasts over Europe and 2 kilometers over Greece. And all this data, all this data are currently provided in a WebGIS service that the user or our co-designer can go. We have some parcels that as a demo currently, that they can go and check all these layers that I just mentioned, the hazard layers from gale, from flood, from temperature, the risks and the vulnerabilities, so they can differentiate their products and tailor them according to the hazards and risks over the area. And they can search with the ID of the parcel. They can search with a coordinate set by manually moving a cursor. So it's designed to be very user friendly. And in terms of forecast, for the parcel of selection, you can see a 10-year forecast of the main atmospheric parameters that affect the quality of this crop type. We will add here thresholds that will clearly denote if we are out of the ranges that affect the crop type. And we have this as a 10-day forecast, as well as a high-resolution 2-day forecast that provides some more parameters to be useful. So
hello?
Mr. Harris, can you hear me? No one's talking?
Hello, looks like... Hello? C'è nessuno?
Angelo, I can hear you.
I can hear you too.
Okay, so I guess that the speaker abruptly shut down his connection.
Yes. I don't know.
But also Aris. Aris, are you there?
Yes.
Ah, okay.
Participants. Yeah. They appear in the participants, but
There may be a technical problem with their connection.
Yes.
Hello, hello. Can you hear? Can you see us now?
Okay, perfect. Now we can hear you and see you.
Okay, sorry for that. We had a technical problem. I don't know how much of the presentation of Nikos you were able to follow.
You lost us in the concluding remarks, right? Or earlier on?
No, just I guess 2 minutes. The last 2 minutes.
Okay.
Should I mention? Do you have enough time to mention the concluding remarks?
Yes, Nikos, please, if you would like to repeat. Okay.
So.
Share screen.
Was it?
Can you share?
All right.
Can you share screen? Share screen. Share screen. Okay, thank you.
So 1 sec. So in order to conclude, I was saying that through this ongoing research of ESAPE project and this pilot, there are services that emerged and provide detailed information to the insurance sector. And the important thing is that this information emerged over a prior data pool region, that future insurance products can be tailored upon each parcel's unique characteristics. There is an early warning system that is a valuable tool in the hands of agronomist consultants in order to effectively consult the farmers' associations. And the combination of this research with ESAPE Showcase 1 Pilot 2 research that provides the current phenological stage of the crop can fuse into an integrated tool that can denote optimum seeding, fertilizing, irrigating, and harvesting conditions, which is very important. And as a last slide, I presented our dissemination activities. We had a presentation in Smart Farming Conference in early October, presenting our research on ESAPE. And we also look forward in early December to present in this year's AGU conference. And the important part is that one of these is more user-oriented, the other one is more scientifically oriented. So we try to expose this research to as broad an audience as possible. So that's it for me. Thank you very much.
Okay. Let me just come back here. All right. Thank you very much, Nikos. Thank you very much for highlighting a smart and user-friendly service which has been co-designed and co-created so closely with the key stakeholder from the agricultural insurance sector. Now we pass to the last part of our session, which is the session of discussion. I don't know how much time we have.
11.
11 minutes.
10,
okay, 10 to 11 minutes. Okay. So I would like to ask a question to all the participants. Actually, it is the same question. Because as you know, the next session that follows is that I have to summarize what are the key points. I mean, as that you have actually reported in the course of your pilot development. So I have to ask the same question to all of you. Which have been so far the main key points to highlight and the challenging points, if I may say, to highlight in the course of your pilot development? I start from Nikos Papagiannopoulos, and I give 2 minutes to each one of you maximum, please, to reply to this question.
Okay, my feeling is that okay, when it comes to alerting for volcanic eruptions, I know that very well the stage is very well set, meaning I think that, for instance, the VACs that I mentioned in my presentation and some other bodies and entities that exist about this, about the safety of aviation, somehow they're interested into voices, strong voices to give a message. My feeling is that with this pilot that we have managed to identify what is needed, what would be useful for them. However, I think that we need somehow to reach out to them, the main users, and see if what we do is important for them, the end users. This is a feeling. Regarding now to what we have managed to do so far, I think we have managed to do more or less to clarify, to have the server working, the server app. We have somehow pinpointed which data we need to move on with. And I think the next crucial point and step is to set up the platform. Either will be the one that I showed you, the one that was implemented for another H2020 project, or a platform that we should develop ourselves. This is my message, and these are my points and comments.
Thank you, Nikos. Thank you very much. Antonio, what is your answer to this question? Hello, Antonio, are you there? Antonio, can you hear us? Okay, Pablo, could you please take the floor and give me an answer to this question, please?
Yes. First, I want to thank Angelo that finally we didn't. I think that we didn't have time to show his presentation that you told me yesterday. I think that in our case, our key point is that we have developed a methodology that is useful for most of the geohazards which are detectable by INSAR data. That's the key point. And now I think that the most problematic thing is to transfer these informations to new stakeholders, because we have developed it in collaboration with our main stakeholder, but at the moment it's been difficult to access to new ones, because sometimes they don't understand good what are we doing, and it's difficult to access them. Perhaps that's that has to be we have to put more effort in that side. I don't know if I'm answering correctly your.
So for you, the key point or the challenging point is what we call capacity building.
Yes.
It's the training of the stakeholder. But okay, this is of course a very important point. But what about the processing of the data? Because we are dealing with big data. Do you have anything to comment on using the right platforms? Like, I mean, before Nico said that for us, key point is to have the platforms available, open and operating always. What is your opinion about that? Because INSAR is taking its very demanding processing.
Mm-hmm. Yes, of course. For us, it's very important to have the capacity to work with GEPTEP. For us, is the main input, and the availability of this product is vital for us. But we have also completed the process to adapt the outcomes from GEP to our methodology. So at this point is not a problem, but the problem is if this GEPTEP platform is not available for us. I think it's.
But as far as that platform is available, do you think it's sufficient for your needs?
Yes,
Okay.
yes. It's very efficient. It's a 2 days process. Sometimes it doesn't work very well, but it's expected in a web processing platform. Now it's okay.
Thank you very much, Pablo. And Nikos, what is your views about the key points or challenging points in your pilot development?
Harris, I would say that, as I already stated in my concluding remarks, I think the key point is that somehow we started providing information over a region where recently nothing was known, and we tried to effectively blend all kind of EO and the numerical weather prediction and whatever kind of information we could get our hands into, and provide a tailored service and detailed information over a data pool region. Across this effort, our main challenge was the availability of in situ data. There wasn't much, and whatever there was not openly available. So I think that things need to move more decisively towards a fully open access of the observational data for research applications. In terms of co-design, we constantly receive feedback from our services by the main co-designer, and our aim, as this product takes shape recently, is how to expand, as I said, our user segment and involve more and more organizations. We already have a good collaboration with ELGA, which is the Greek Agricultural Insurance Organization Public Authority. We also discuss with milling agencies. This is our main target. So in terms of openness, this web service that we have created is currently open to display to whoever is interested. And we also feed our results to our partners' platform, which is GEOSS. So we have both an open and more closed approach, but we prefer to have this as open as possible in general.
Okay, thank you, Nikos. Thank you all. Is maybe Adonio there to give also a reply to this answer? It seems that Adonio is either not there or there is a technical problem. So let me sum up. Up to now, what I have taken as a note from what you just said is that the main challenging points are platform, having the platform available and up and working, platforms that are available there for processing big data or different combinations of data, not only Earth observation data, in situ data, radar data, sensor data. The capacity building issue seems to be very important, of course, but this capacity building comes along with the co-design. So this is why actually the co-design process has been included in the ISA, because we knew from the past that, of course, it's not an easy task to make the users trained or learning using the services from one day to the other. Important is also to see that we are in the new era of blending Earth observation data with in situ data in completely unknown environments. I keep the term that used by Nikos, which is indeed very important, because we have a lack of in situ data, or at least not in line data from Earth observation with in situ data, or data which diachronically have been collected that have to be reported or let's say retrieved from Observatory and used for our services. As 3 points to be reported, at least after your presentations to the next session, is that first, that we are supporting the daily practices of civil protection authorities, but at the same time of sectors of industry, of economy drivers like agriculture, energy, critical infrastructure, facilities management industry. The second point is that I have reported is that we are today already to some extent successful in generating enhanced information delivered by assimilating many different types of data, Earth observation data together with in situ data, together with sensor data. We had very good examples here. I mean, it was the example of Antonio's presentation, of Nikos' presentation, and we have several good examples to showcase. And the third point is the need for our pilots to migrate towards exploiting existing platforms for the processing of big data, but also exploiting platforms for retrieving in situ data. And we had already some good examples. For example, Antonio presented the use of radar or in situ meteorological stations, but also Nikos presented the use of ACTRIS data, ACTRIS in situ European infrastructure, which is seems to be very useful for his for the delivery of its services. Nikos also presented the use of ERA5 data in providing useful knowledge for the agricultural insurance sector. I don't know if you have something to add on these main points that I have reported so far to be presented in the following section. But please, the floor is yours. Please feel free to tell me what else you think is most appropriate to report, because you are actually the ones developing the pilots. You are the ones that have to speak to me in order to prepare myself in the next session for presenting your key points. Please take the floor one by one. Nikos, what do you think? I mean, do you agree with what I just presented? Do you think something else to be added?
No, I fully agree with you. At least our worry was that you already mentioned, and I think you will convey this message. I think I don't have anything to add up to that.
Okay, very well. Thank you. So one by one, then Pablo.
Yes, I also agree. I think the conclusions are very interesting for all the other showcase leaders. So.
And Nikos, what is your opinion?
Harry, I agree with what you said, and I have to say that this is a very interesting phase of the project, because after 1.5 years of hard work, it starts to flower, and we see that the services are developing in all pilots, and it is currently at an interesting phase to see services emerging and interesting research to be communicated. So,
okay, I do see a note here that someone referred to the co-designing process, and this is very, very important for the ISA. It is the first time in a European Union project, such a big project, I mean, with so many pilots, that we have adopted the process of co-designing. And the co-designing process is that the one that will help us for the next day. The next day that at the same time we do capacity building, that we build at the same time services for the needs of the stakeholders. So please continue. Do co-design and co-create services together with the stakeholders. Do not forget that as scientists, many times we take over the responsibility for everything, but this is not true. This is not the real life. The real life is that we speak and work together with the co-designers. Having said that, I would like to thank you all for your interesting presentations. You gave me a lot of food to present next session of the PMT and the plenary session, actually. And once again, thank you very much to all for your kind attendance. Thank you.